Okay, this is going to be the first of a three-part video on substitution reactions, chapter 8 in the textbook. Okay, so this equation at the top is a generic nucleophilic substitution reaction. We have three basic factors going into this. We're reacting some sort of nucleophile. Often it has a negative charge, like I've indicated here, an alkyl halide, and it's reacting in some sort of solvent, and in the process the X group, the halide, halogen, is going to be replaced by whatever the nucleophile is, and the halogen turns into the halide anion. Okay? If the later cases in the class, we're going to encounter situations where the nucleophile is neutral, and if the nucleophile is neutral, the substrate, or the product here, which I'm just abbreviating that way, would then have a positive charge. Okay. All right, so in the most of the commonly used nucleophilic substitution reactions, this is the rate equation here. Rate depends on the concentration of the substrate and the nucleophile. This is known as the SN2 reaction, which stands for substitution nucleophilic second order. About half of this chapter is going to be devoted to a discussion of the mechanism for the SN2 reaction and trends in the SN2 reaction on how the substrate leaving group, nucleophilicity, and solvent all affect the SN2 reaction. After discussion of the SN2 reaction, we're going to look at another type of substitution that goes by first order kinetics, known as SN1. It's not quite as common, or not quite as commonly employed as the SN2. And then we'll look at the SN2 and SN1 in competition with previously introduced reactions in Chapter 5, Elimination Reactions. Okay. So here's a chart of common nucleophiles. This is not an exhaustive list. This is just some of the most common ones that you see in organic chemistry. So in this table, we have the nucleophile, and over here on the right, we're going to have its conjugate acid and the pK of that conjugate acid, so we can get a relative idea of the basicity of this nucleophile. All right, so the simplest nucleophiles we have are halide anions. Okay, and these are, of course, not very basic at all. They're derived from strong acids, except for HF, which is a much weaker acid. Okay, alkoxide and hydroxide nucleophiles, which are the conjugate bases of alcohols and water, respectively. We're going to see many examples of these. Carboxylate nucleophiles are the conjugate bases of carboxylic acids, which have pKa's normally 3 to 5. Thiolate and hydrosulfide, these are the anions of thiols and H2S. These are derived from conjugate acids with pKa's of 9 to 11. Cyanide anion, we'll see many examples of this. This is probably the most common one we'll see in the equations that I present. It has a pK of 9. And the azide anion, derived from hydrozoic acid here, has a pK of 5. This is a latter one. You've probably never seen anything like it before, but we're going to find it's a very useful way to introduce nitrogen into organic compounds. Okay, so let's look at a sample equation here. What's going to happen when we treat this compound in the middle here, allyl chloride, with various nucleophiles? Okay, so a reaction with sodium iodide is going to turn the chloride into the iodide, reaction with cesium fluoride. We use cesium in this case because in fluoride it's best to have as much ionicity as possible, and cesium is below sodium and potassium in the periodic table, so this is about the most ionic bond in all of chemistry. Okay, and this will give us the fluoride. Treatment with the alkoxide is going to give us the ether. This is a reaction that we will revisit in chapter 14. It's called the Williamson ether synthesis. Okay. Reaction with the thiol is going to replace chloride with the S and whatever came with the S, in this case a cyclopropyl. Here I'd just like to point out that you should never be confused by us presenting it as a minus or with a sodium as a counterion, okay? You have to understand that the sodium-oxygen bond is an ionic bond, as would be probably the sulfur-sodium bond, and it should not make any difference to you whether we present this equation as a nucleophile minus or the nucleophile associated with a counterion. Okay, and you'll see it both ways presented by virtually every organic chemist. Everybody presents these things differently, so you just have to get used to seeing it both ways. Okay, with the benzoate anion shown here, this is a carboxylate anion. We're going to make this type of compound known as an ester. Cyanide is going to turn chlorine into CN, and this will give us the nitrile. N3 is going to turn chlorine into N3. The azide anion is going to give us that. Okay, let's just look at the names of these functional groups since we've not had them before. This is an ether. This is a sulfide. This is an ester. This is a nitrile. And this is an azide. Okay. I just want to say one more thing here. One of the worst answers I get often on exams for questions like this would be this compound here. And if sodium or whatever the counterion is, be it lithium or potassium or magnesium or something like that, ends up in your SN2 substitution product, you clearly haven't analyzed this equation right. It's only the anionic part that ends up in the nucleophile. I would love to have an exam where I don't get any answers like that, but in 30 years of being a teacher, I have yet to achieve that goal in any class. But so don't have your counterion end up in your SN2 product. Okay? All right, so let's look at solvent issues first. Okay, when you're thinking about an SN2 reaction, there's of course a dilemma. Your alkyl halide wants a nonpolar solvent. Your nucleophile, often an ionic compound, does not want a nonpolar solvent. It wants a relatively polar solvent. We have to have a solvent that can dissolve both of these. The best solvents for the SN2 reaction are referred to as polar aprotic organic solvents. Okay, one of the best ones is the first one shown here, called dimethyl sulfoxide. It's incredibly polar because of this dipolar resonance structure shown here, and it's abbreviated DMSO. Another really good one is N-dimethyl formamide, or DMF. Because of this important resonance structure here, let's just go ahead and draw the arrows. Oops, arrow was a little bit off there, sorry. This ends up being also a very polar compound. Acetonitrile, shown here, has a very strong dipole, and that accounts for its polarity. Also, good polar solvents are acetone, and sometimes it boils a little low, around 55 degrees C or something like that. Sometimes you need a slightly hotter temperature than that, so 2-butanone or methyl ethyl ketone, MEK is the abbreviation for methyl ethyl ketone, are often used as polar aprotic organic solvents. What about polar protic solvents like alcohols? Well, the problem here is that they stabilize the nucleophile through hydrogen bonding, as you can see with this structure here with the azide, where it's hydrogen bonding with methanol. This makes the azide less of a free anion and stabilize it, and thus decreases its reactivity somewhat. The SN2 reaction still usually works in these solvents, but it's not quite as fast as it is in these solvents that are aprotic. Okay. Let's look at relative reactivity with respect to leaving group. Okay. And this is true for almost all of the halogens and most of the reactions that they do. The relative reactivity is that the iodide is the most reactive, more reactive than bromide, more reactive than chloride, which is far, far more reactive than fluoride, and fluoride is, for all essential purposes, useless in this reaction. Okay, two issues account for this trend. One is that the carbon-iodine bond is the weakest. The bond strength to carbon decreases as you go down the periodic table for most of the elements on the right side of the periodic table. Okay, so this is the weakest bond. It's the easiest one to break. Also, iodine is the best leaving group because it's the weakest base. Recall that for the acidity, HI was the strongest of these acids, meaning that the base strength is going to be opposite, and iodide is going to be the weakest base. This latter effect is probably more important because we're going to encounter oxygen-based leaving groups that are comparable to iodide later in this chapter. Okay? All right. This is probably the most important trend, relative reactivity with respect to the structure of R. R is methyl, greater than primary, greater than secondary, greater than tertiary, which is, for all intents and purposes, very few successful SN2s for tertiary systems. Okay? This is strictly a steric effect. And you can sort of understand that when you see the mechanism. This is the generally accepted mechanism for the SN2 reaction. It's called concerted one-step backside attack. The nucleophile, in this case cyanide, approaches the backside of the carbon that's undergoing the substitution. In this case, we're using ethyl bromide as our substrate. Okay, so it's approaching the backside. So cyanide is on the side opposite where the bromide used to be. Bromide is now displaced, and we get our product. Okay, if you notice here, this is going with inversion of configuration. This case here, it doesn't matter because the compound's optically inactive, but we're going to see in the next slide how or actually in a few slides ahead, how that can matter. Okay, there's no actual intermediates, no carbocations, no free radicals, no cute little things like that, but we do have a transition state. And here's the transition state. It's basically as the cyanide is coming in, the bromide is going out at the same time. We can think of this as kind of like a carbocation with two nucleophiles partially bound to it, or two anionic species partially bound to it at the same time. You're probably saying, why is it my instructor can get away with drawing 5 bonds to carbon, but I can't? Okay, this is because your instructor has very carefully indicated that this is a transition state. This is not a stable compound. This is the highest energy point along the reaction pathway. Okay, and recognize that I'm not really drawing full distinct bonds. I'm drawing partial bonds here. So this is a partial bonding. That's what that symbol indicates. Okay. All right, so what's the reason for this steric effect? The reason is that the methyl group typing in CH3 does not do true justice to the size of the methyl group. It's a blob of electron density with the CH bonds, and it's whirling around in space. I'm going to give it a circular shape. I'm not sure that's completely accurate, but this diagram here sort of illustrates the point. All right, in ethyl bromide, the methyl group's offering a little bit of a hindrance to the pathway here. Perhaps it's interfering there, so this accounts why ethyl bromide would not be quite as reactive as methyl bromide, which just has a hydrogen where the CH3 is. However, when you put 3 of these CH3 groups here, you find that it's very difficult for the nucleophile to approach from the backside. The backside is almost completely blocked from any sort of approach, okay? All right, so this accounts for this important trend up here. Methyl greater than primary, greater than secondary, greater than tertiary. I'm going to add also, this is the first time that alkyl substitution has hurt a reaction, right? In all of the previous reactions you've seen double bond additions, carbocation stabilization, free radical stabilization, double bond stability. Alkyl groups have always helped you or made the system more reactive. This is the only case, or the first case you've had, where they make the system less reactive. Okay, let's look at some other effects. Substitution on the beta carbon, if we call this the alpha carbon, we're going to call this one the beta carbon. Okay, it's going to have a lesser but a noticeable effect. Okay, so what we see here is that the N-propyl isn't quite as reactive as the isobutyl, which has at the beta carbon, an extra methyl group. Okay, when you actually completely substitute the beta carbon in what we call a neopentyl system here, the SN2 reaction becomes very difficult. This group out here is just so large that it's very difficult to do an SN2 reaction. So it's tertiary systems and neopentyl systems which are practically inert in the SN2 reaction. The other structural limitation we're going to point out here is that you can't do the SN2 reaction at sp2 carbon. Okay, bond strength to the halogen is greater and the backside is quite hindered. Okay, so if you imagine the nucleophile approaching here, this hydrogen is kind of stuck out here in the place where the nucleophile needs to migrate by. So for that reason, we don't see substitution at these types of carbons. They might undergo substitution by other mechanisms, but they never undergo substitution by an SN2 mechanism. Okay? All right, so here's a problem for you. Rank the following compounds as to their relative reactivity to cyanide and DMSO, which is a typical SN2 reaction. You're just ranking these in their ability to undergo the SN2 reaction. Okay? And I'll just say, just for fun, draw the products of each of them doing the conversion. All right, so you should go ahead and do this, pause the video, and then restart it, and you'll see the answers. Okay, so what we would want to first do is look at the types of halides that we have here. Okay. So we have a secondary, a tertiary, 3 different primaries, and one that has a halide at the sp2 carbon. We can probably say this one here is going to be our worst one based on the statement last time, right? Okay. All right, so what's our best? Okay, so leaving group trends, iodine is better than bromide. If we have 2 substrates where the only difference is iodide versus bromide, we should go with the iodide as being the more reactive one. All right, so our most reactive one is going to be the primary iodide, shown here, that does not have any beta substitution. Okay, the next most reactive one is the one immediately to its right, followed by the other primary one that has beta substitution, followed by the secondary, followed by the tertiary, followed by the aryl, or the compound that has bromine at sp2 carbon. Okay? All right, so this is our trends. These are our products. Recognize that our fastest and our second fastest both produce the same product. I might add that number 5 and number 6 the yield is probably 0% for both of them, okay? I don't think that you get very much of this from either of these reactions, but a tertiary system does have some capability of doing the SN2, whereas the halide at sp2 carbon really doesn't do the SN2 reaction at all. Okay. All right. Here's this. We said something about how the SN2 would go with inversion of stereochemistry, but I didn't have an optically active starting material. Let's put an optically active starting material. So let's start with the simplest chiral compound of them all, R2-bromobutane. Okay. I think that's R. Yes, it looks R. Okay. Cyanide is approaching the backside, right? And that means that we see this inversion here, okay? In this case here, cyanide is on the left side, whereas bromide was on the right side, and it causes the basic orientation of the ethyl, methyl, and hydrogen to invert, kind of like an umbrella in a windstorm. You can think of that as being an analogy here. And what you see is an inversion in that R converted to S. You always have to be careful that R to S is really an inversion, because there can be a change in priority numbers, but in both of these cases, bromine and cyanide both are the #1 priority, so we can say with absolute certainty that this is a true inversion of configuration. Okay, let's look at some examples. So for example, if we took a compound where the halide has some definite stereochemistry, like this cycloheptyl iodide with a methyl group here, we could predict that the product of any SN2 reaction ought to be the product with inversion of configuration. And you see that right here. The reaction with the thiolate produced the sulfide with inversion of configuration. The reaction with sodium azide produced the azide with inversion of configuration. An interesting thing happens when we use iodide as the nucleophile. Here the nucleophile and the leaving group are identical. And what we see here is that our first iodide is going to invert the configuration, However, our second iodide is going to invert it back. So we see here, when we treat it with this iodide, is a scrambling of stereochemistry, and this is a common mechanistic technique to look at the rate of scrambling relative to other reaction rates to determine if something is SN2 or not. Okay, maybe we'll see an example of something like that later. But what we see here is that we're just isomerizing the stereo center when we treat this with iodide anion. Okay, I think this is where this video ends. No, sorry, we're going to talk a little bit about the other factor here, the nucleophile strength, nucleophilicity. Okay, so two factors can lead to enhanced nucleophilicity. Nucleophilicity parallels basicity. The best nucleophile will be the strongest base, or the best nucleophile will be derived from the conjugate acid with the highest pKa. Nucleophilicity also increases with increased polarizability. I'll try to explain that. That's one of the more difficult concepts to explain, but the net result is that nucleophilicity or polarizability increases as you go down a column of the periodic table. And we're going to see that the second trend is actually the more important one. First, let's look at an example of the first trend. Okay, if we compare oxygen-based nucleophiles, we can just look at the pK of the conjugate acid to determine which is the nucleophile, which is the best nucleophile. Okay, so ethoxide is a better nucleophile than acetate, which is this anion here, which is the conjugate base of acetic acid. And this is a much better nucleophile than just plain old neutral water, which is the conjugate base of H3O+. I'm not sure what its pK of H3O+ is. I'm going to say it's -4 or something like that. But it's a number much lower than 5. Okay? Alright, so the relative reactivity with methyl iodide to make methyl whatever the nucleophile is would be ethoxide faster than acetate, faster than water. Here, when we compare the same atom being nucleophilic, we see pretty much an exact correlation between nucleophilicity and basicity. Okay. But a more important factor probably is the polarizability. All right, so I'm going to say over here on the right, I have just a sphere, and this is what we're going to call our negatively charged ion out in space with nothing around it. But this negatively charged ion is going to distort its shape if something with a positive charge comes in its vicinity. And so we're going to have a partial positive here at carbon because it's bound to a halogen, okay? And this negatively charged nucleophile can now distort its shape to put more of the electron density closer to the partial positive charge. So it's the negative charge is going out to meet the positive charge. The ability to distort this electron cloud around a negative anion to adapt to its environment here is the polarizability. Okay, and the larger or more diffuse the anion is, the more easy it is for it to distort the shape of the electron cloud. I always like to say that you can think of a fluoride anion as being like a golf ball, and a iodide anion as being like a water balloon in its ability to change its shape to adapt to the environment. Okay, because it can do this, of course, it has an easier time going out to meet the positive charge and making this bond to the partially positive carbon. Okay. All right. So here we see that a classic comparison is thiolate versus alkoxide. Thiolate is the better nucleophile. And this trend is opposite to basicity. Remember, the pK of thiol is about 10, whereas the pK of methanol is about 15. Okay? So the alkoxide is actually the stronger base, but the thiolate is actually the better nucleophile. So here's a case where nucleophilicity does not equal basicity. They're working in opposite directions. And you see how the polarizability issue or the periodic table trend was the more important trend. So amongst the halogens, the iodide ion is by far the best nucleophile, despite the fact that the fluoride ion is far more basic. And this exists for the other columns of the periodic table too. Phosphorus things are better nucleophiles than the analogous nitrogen things usually. Okay, so we're going to do a final nucleophile ranking question before we end this video. Rank the compounds in terms of their relative nucleophilicity. The pK of the conjugate acid is in parentheses. Assign number 1 to the most nucleophilic one, number 4 to the least nucleophilic one, number 2 and 3 wherever they lie. Okay? All right, so again, do this and then restart the video and you'll see the answers. Our most nucleophilic one is the compound here. Okay? And this is because it's nucleophilic at sulfur, and of the two compounds that are nucleophilic at sulfur, this is the more basic one. Okay, so when we compare sulfur with sulfur, we go with the more basic one. This is number 1, this is number 2. Now we're comparing oxygen with oxygen. The pK of cyclohexyl alcohol is 18. The pK of acetic acid is around 5. So the alkoxide should be a better base than the acetate. There's such an extreme difference in the pKs between 2 and 3 that it might be a difficult call, but I always construct exams and quizzes so there's never any ambiguity like this. Okay, this is the way you should rank them. The polarizability issue is more important than the basicity issue. Okay. But when the polarizability issue is equal, then you do consider basicity. Okay. All right. So this is where we're going to end this video here. We'll talk about the SN1 reaction in the next video.